Welcome to reinforcement learning, and now we're going to learn how to take actions based on predictions. So Markov processes are a description of how to do transitions from one state to another state. And here we have in circles the states, and the circles denote that we look at random variables. And the probability to end up in the next state is determined by the last state that we have been in. So this is a first order Markov process that is stationary as well. And we want to augment this model with actions. And the actions are put in boxes and squares to distinguish them from the random variables. And now you see that there is an arrow pointing from those actions to the next state. So that means that the actions also determine where we end up next. So you can imagine a robot trying to take the action, I want to go right, yeah, and ending up right as well. Or it might be, because we have here a stochastic process, that the robot says, I want to go right, but it ends up going straight forward. This model actually is stochastic in that sense, and also needs some description of how good the actions were and how good the states are in order to learn. So the state action pair actually gives us a reward, and that's in a diamond, and this diamond shows that this is some measure of utility or value or a reward or profit. Now, the Markov decision processes have stochasticity, and they are also sequential over time, and we will keep these assumptions later on. But because they're the foundation of much of reinforcement learning, and we will later see how the algorithms actually will work in these through the lens of the Markov decision models, we will now get a deeper understanding and use some assumptions that we relax later. So we will assume for now that we observe all the states, and also that we have a complete description of the model. That means we have the transition matrices, so we know the transition model, and also we know the reward function. Yeah? So later we will learn exactly these objects. And also we assume that we have a discrete action and state space. However, later we will see how we can deal with continuous actions and continuous states. Now, a Markov decision process is defined by a set of actions that we denote by capital A, and a set of states, that is capital S, and also a transition model that we now assume to be known, which is the probability to end up in state st, given that we have been in state st minus 1. And now we augment this also with the action at minus 1 that we have taken. And also we have a reward function. The reward function depends also on the state action pair. And the goal is to find the optimal policy and to find algorithms that can help us to optimize our policies. Now, to understand how we can model this and how the algorithms can be set up, we need to think about what are the rewards and what are values, and how can we use discounting in this context, and why we would use that. Now, first let's think about what are the rewards. The rewards are a numerical signal that we get from the state action pairs actually, and it can be any real number that we get when we take a specific action and are in a specific state. Commonly, these reward functions are assumed to be stationary. That means they're the same at each time step. Yeah? But it could be also that they differ. Yeah? So, for example, if you think of playing a game, like a chess game or a game of Go, then in every turn you have a reward of 0, and only at the end of the game you know whether you won or lost. So for the learning, you need to see then the reward at the end of the game that is capturing all your moves. The complete sequence of moves that you made are then captured in this +1 or -1. And also this reward function, so this looks here or is written up as a deterministic function, but the rewards could be stochastic as well. But if you think about expected reward, then this is something deterministic, and that's the reason why people commonly use this reward function in this way. Now the idea is to maximize the sum of total rewards over a long time period. So imagine you're a business owner and well, you don't want to go bankrupt, so you have an infinite horizon problem. And well, if you earn profits in every period, then your rewards will be infinite if the process is infinite as well. So that poses some sort of problem to find the optimal policy. And so because of that, we discount future rewards. So that's the solution to make this infinite horizon problems tractable. But it's also very intuitive. So if you think about profits 10,000 years ahead versus today, the same profit, well, you would probably attach a lower weight to the profit in 10,000 years than the same profit today. And that's the idea of the discount factor, which is a number between 0 and 1. And this actually weights the future rewards with a geometric sum. So the sum of discounted rewards will then be something that gives you finite utility. And the gamma, the discount factor, actually induces a per period time preference rate of 1 over gamma minus 1. So that's a measure of how much you value future profits or rewards versus rewards today. Now, with these additional parameters, we have the Markov decision processes a little bit more described. So we have here the discount factor that can be used to discount if it's lower than 1 and greater than 0, or undiscounted if it's equal to 1. And we have also two cases with respect to the planning horizon. It can be infinite or finite. And the goal is to find some algorithms that help optimize policies. Now let's consider an example from inventory management. And here the idea is, well, imagine you're a business owner, you have a warehouse where you have some goods that you produce or that you buy, and then you want to sell them. And so the problem is that sometimes people come and want to buy something and you don't have that in stock. So you miss a sale, and that would be bad for your profits if that is systematic. On the other hand, if nobody comes and you have a lot of goods in stock, then you lose also out because you have to pay rent and heating for the storage, and it's costly. Now, the states in this Markov decision process are the inventory levels, so your stock of supplies. And the actions that you can do is either you do nothing or you order some goods. Now the demand is stochastic, but a stationary transition model. And the rewards are then the sales. So we sell the goods, sales, the number of goods times the price, minus the costs of producing them or buying them, and the storage costs. And because we don't want to go bankrupt, we want to make profits forever. We have an infinite horizon problem, but we discount with a number just below 1, 0.999, just to make this tractable. Now, well, we have the trade-off of increasing supplies, which reduces the odds of missing sales, but also increases at the same time the storage costs. So we want to find some algorithms that can help us to maximize the cumulative rewards. Now, to do that, we need the best policy. And what is a policy? That would be the next question. So basically, a policy is a choice of action at each time step. Formally, we can write this up as a mapping from a state to an action. And we write that up as pi. Pi is the policy given a state st. And that actually, if we have a Markovian stationary process and everything is fully observed, then this state has all the information that we need to know the right action. And so there's a clear mapping from the state to the action, and that's the policy. And so if we actually are in state S0 and plan ahead h periods, then how we can evaluate policies, so a sequence of actions, we can write this up as expected utility, and that's this V of pi, of the policy pi, given the state S0 where we are and plan ahead, and then we sum up the discounted expected rewards and the expected rewards in each state. So that's why we need the transition model here and the reward model, and that's the things that are known now, and that's the things that we're gonna learn later in the reinforcement learning algorithms. Now, the optimal policy is that sequence of actions that gives us the highest expected utility, and so that would be then the V pi star. That's the best one. That's better than all the others. Now, there are several classes of algorithms that can solve these for these optimal policies: value iteration, policy iteration, linear programming, search techniques, and also this optimization can be done offline. So we plan before we actually start what are the policies that we want to do and optimize them, or we do it online, so when the process is ongoing. Now, here are some references on the Markov decision processes, but let's summarize what we have seen today. So we have seen that Markov decision processes extend the Markov processes with actions and rewards, and they help us to find a policy that maps states to actions with the goal to maximize the expected cumulative rewards. And the policies can either be optimized via value iteration, policy iteration, or other algorithms. And discounting helps us to handle infinite horizon problems and to capture time preference for earlier time periods. Thanks for watching.